All right, we've got 2019, number 2. The velocity of a particle p moving along the x-axis is given by the differentiable function v sub p, where v sub p of t is measured in meters per hour and t is measured in hours. Selected values are shown in the table above. Particle p is at the origin at time t equals 0. All right, justify why there must be at least one time between 0.3 and 2.8 where the derivative of v sub p, the acceleration of the particle p, equals 0 meters per hour per hour. All right, so with a derivative, or with this, we're essentially looking at the second derivative, right? This is already the derivative of the position. We're looking at the derivative of velocity, which is acceleration. And we want to see why that needs to be equal to 0 at some point in there. So the crucial things, essentially, we're going to find an average rate of change. So the average rate of change on the interval 0.3 to 2.8 is the value of the function at 2.8 minus the value of the function at 0.3 over 2.8 minus 0.3. So this is 55 minus 55 over 2.5. This is the average rate of change, which is 0. So on this interval, the average rate of change is 0. Since the function is differentiable on that interval, then by the mean value theorem, there must be a point in that interval where the instantaneous rate of change is equal to the average rate of change. So average rate of change equals 0. The function is differentiable, so there must be a point in the interval where the instantaneous rate of change is equal to the average rate of change. For b, use a trapezoidal sum with 3 subintervals to approximate the value of the integral from 0 to 2.8. All right, so we want to find the integral from 0 to 2.8 of v sub p dt. We're going to do this with a trapezoid, so we're breaking this into 3 pieces. We will have 0.3, the width, times the average height, 55 plus 0, the width, 1.4 times the average height, 55 minus 29, and the width, 1.7 to 2.8 is 1.1 times the average height, negative 29 plus 55 over 2. Alright, so you type all that in, you get 40.75. That's really all there is to that one. C. A second particle, Q, also moves along the x-axis so that its velocity between time 0 and 4 is given by that. Find the time interval during which the velocity of the particle is at least 60 meters per hour. Find the distance traveled by particle Q during the interval when the velocity is at least 60 meters per hour. Alright, so we're going to our calculators for this one. And let's type this in. So I have 45 x, the square root of x, whatever. And cosine of 0.063 x squared. We want to, okay, So our window is going to be x is between 0 and 4. 0 and 4. I don't know the max value, but we're going to at least 60. Let's go to 100. Right, like we want to see where it's at least 60. So we'll try 100 as kind of a guess. Oh, I should actually, before we do this, let's go like this and graph a second one at 60. Then we can see where it's above the line. That will be when it's at least 60. Okay. So now we can find the intersect of the first curve and the second curve. .8661815. 1.8661815, and we want to find the second one. First curve and the second curve, but we need to find the other one, so we need to go over and that one is 3.5191744. Alright, so if we write those down, it's going to be between and so that is the time interval. That was question number 1. Find the distance traveled when it is at least 60 miles an hour, meters an hour, sorry. We're going to take the integral from 1.8661815 to 3.5191744 of our function v sub q of t. This is an important step. You need to write that down. You're going to evaluate that with your calculator, but you should write down the integral as well. So let's find the integral from 1.8661815 to 3.5191744. $106.10875. So technically, actually, what we should have done is taken the absolute value because we're interested in distance traveled, but like it's all greater than 60, so we don't really actually care about that. Anyways, D, at time 0, particle Q is at position -90. Using the results from part B and function Q from part C, approximate the distance between particles P and Q at time 2.8. Alright, so we know a couple of things. The position of particle D. So the position of particle P of P, let's use S of P at 2.8. This is what we got from part B. So let's erase that. It looks like a not equals to is equal to 40.75. That is what we got right up there. The position of particle Q at 2.8 is going to be the integral from 0 to 2.8 of V of Q, V sub Q of T, plus our initial position. This one is technically plus 0 because that was our initial position for particle P. But yeah, that's just plus 0. This one we're going to find the integral and subtract 90. So let's do that. Alright. trace an integral 0, 2.8. What's going on? Yeah. Let's go window, okay. I don't know. Clear draw? Does that do anything? Okay, there we go. Integral. Is it because I start at 0? It might be because 0 is not in the window. Let's try this. Oh. Is this that shouldn't matter. Oh, yeah, it's for that one. Yes. 0. 2.8. Still being weird. Alright, let's try the other one. Yeah, quit. Math. F and int. 45. Square root of x. Cosine of 0.063 x squared. All my parentheses are closed, comma x, comma 0, comma 2.8. This would be better anyhow, because then I can just subtract 90. Maybe it is really being weird. I mean, it's because, no, it's not undefined. It'll just be 0 at 0. Yeah. And then minus 90. So that's where that is. And the other one was at 40.75, so the distance apart, minus 40.75. All right, so we should write all of that down, really. Okay, so that was at 45.9376535. Distance apart equals 45.93765 minus 40.75, which is 5.1875.